Physics problem related to Snell's law. In the problem, a light ray with a wavelength of 498 nanometer traveling through air is incident on a smooth, flat slab of glass flint at an angle of 32 degrees to the normal, as sketched in the figure below. At what angle does the ray of light leave the glass flint as it enters the water? Letter B. What is the energy of the wave before it enters the glass flint? So, this is the illustration of the problem. So, we can see that in the problem, we have three different medium. First, we have the air. Second medium, we have the glass flint. And third, we have the water. And the given angle of incident is 32 degrees. Now, what we need to find out for letter A is the angle of refraction when the ray of light leave the glass plane and enters the water. So to complete the given variables, we can make use of the following table. For the glass plane, we have 1.66 index of refraction. For water, we have 1.333. For air, we have 1. So, this will be the final given in the problem. For the wavelength of the light ray, we have 498 nanometer or 4.98 times 10 raised to -7 meters. So, we convert nanometer into meters. Now, our angle of incident is 32 degrees. For N1, which is the index of refraction for air, we have 1. For N2, index of refraction for glass plane, 1.66. And for water, our index of refraction is 1.33. And we are asked to find in letter A, angle of refraction when the light ray leaves the glass plane as it enters the water. And for letter B, the energy of the wave before it enters the glass plane. Now, for the first step, we need to first calculate the angle of refraction from air to glass plane. So, we will first calculate the angle of refraction from air to glass plane. So, we can make use the Snell's law, where N1 times sine I is equal to N2 times sine R. So, rearranging the equation, our final equation to solve for the angle of refraction is sine R is equal to N1 times sine I divided by N2. Substituting the given variables for N1, we have 1. For angle of incident, we have 32 degrees. And for N2, we have 1.66, which is the index of refraction for glass plane. So, applying the operations, 1 times sine 32 divided by 1.66, the answer is 0.319228472. Getting the inverse sine of 0.319228472, the angle of refraction will be 18.62 degrees. Now, now that we have the angle of refraction from air to glass plate, we can make use this information to get the angle of incidence from glass plane to water using the concept of alternate interior angle, where angle of refraction will be now equivalent to the angle of incidence from glass plane to water, which means we can proceed to our second step, so we can calculate the angle of refraction from glass plane to water. Again, we can make use the Snell's law to solve this problem. Rearranging the equations, we have sine r is equal to n1 times sine I all over n2. Substituting the values, this time our n1 is the glass plane, which is 1.66, and for our angle of incidence, this time we will make use of 18.62, since this is also equal to the angle of refraction that we have calculated a while ago. Again, this is the concept of alternate interior angles. Now, for N2, we have the water, which is 1.33. This is the index of refraction of water. Applying the operations, 1.66 times sine 18.62 divided by 1.33, the answer is 0.398512484. Getting the inverse of 0.398512484, our final answer for the angle of refraction is 23.48 degrees. So, this will be our final answer for the angle of refraction when the light ray leaves the glass flint as it enters the water. Now we can proceed to answer the letter B, which is the energy of the wave before it enters the glass plane. To solve this problem, we can make use the wave equation, where V is equal to wavelength times frequency. So, rearranging the equation, we need to calculate the frequency of the light ray. So, frequency is equal to V divided by wavelength, where V is the speed of light before it enters the medium or the second medium divided by the wavelength. Since our medium in the first situation is air, then the speed of light in the air is 3.0 times 10 raised to 8 meters per second divided by the wavelength of the light ray, which is given in the problem, 4.98 times 10 raised to negative 7 meters. Now, the answer for the frequency is 6.02409638 times 10 raised to negative 14 hertz. Now that we know the frequency of the light ray, we can now proceed to our fourth and last step, which is to calculate the energy of the light ray before it enters the glass plane, which means we can use the equation of E is equal to HF, where H is the Planck constant that is equivalent to 6.626 times 10 raised to negative 34 joules times seconds. And for the frequency, which we have already calculated a while ago, 6.024096386 times 10 raised to negative 14. Getting the product, the final answer for the energy of the wave before it enters the glass plane is 3.99 times 10 raised to negative 19 joules. So that will be the final answer for the problem. For letter A, we have angle of refraction is equal to 23.48 degrees. For letter B, the energy of the wave is equal to 3.99 times 10 raised to negative 19 joules.